This MSE 5033 Composite Materials lecture number 5. So here we are going to be talking about the kinds of interfaces that you can find in different kinds of polymer matrix composites. Um, and we will also talk a little bit about interfaces in ceramic matrix composites, but we will be doing that more in the later classes. But here we will talk about interfaces in glass polymer composites, aramid polymer composites, polyethylene polymer composites, and carbon polymer composites. So most of the time in fibers, you will find that they use what are called silane coupling agents, and this is uh, what you will find is that this is a standard format RSIX, where X has a subscript of 4 minus n, and if n is equal to 1, then it gives you RSIX3, and it is a R is a resin compatible group such as ethoxy, methoxy, or acetoxy, etc. And X is an organofunctional group that is involved in the reaction with the inorganic substrate. So here is a schematic of the type of what we call a chemical bridge. This is mainly in the case of uh, glass fiber composites, and you will find that it helps to create the bond between the glass and the polymer network of the matrix. Now, this itself is not going to be extremely strong because these are not going to be very well attached to the substrate itself, but they will have some reasonably good strength. Okay, and in the case of the interface, there are internal stresses generated at that interface due to the curing shrinkage and CTE mismatch. And they are usually relaxed by breaking and remaking of the bonds under they have what is called a shear dynamic equilibrium. And this bond model is named after a person called Pludeman. Okay, so what you will find is that you have a, in this case you can have um, three types of bonds, and they would shift from one kind of bond to the other, and they would still remain strong. So you first have the R group with the M group, and then once it breaks, if it is sheared, it will go to the next one and still hold on to it like that. Now, many times what you will find is that the fiber polymer interface is not a very strong bond. And in the case of aramid fibers and polymer interfaces, the fibers are extremely smooth, and they do not have many bonding points with the matrix itself. So the interface that you apply as a coating, as a, the uh, in the case of silane coupling agent, it creates the bond between the aramid fibers and the polymer interface, polymer matrix, and but in some cases it is not as strong because of uh, as depending upon the type of fiber. For example, in the case of the aramid fiber epoxy, its interfacial strength is about half that of glass epoxy or carbon epoxy composites. Typically, carbon epoxy composite interfaces are much stronger than the other types of fibers and matrices. And the reason is that there is the there is some amount of heterogeneity between the skin and the core, and the chain is also highly oriented. So if you break the chain, you cannot put it back together, or it doesn't really work well together. And the other reason is also that some of these high strength, high stiffness polymer fibers have very smooth surfaces that show very low reactivity, or they have very low surface energy. And this is also very similar to the types of surfaces that are found in some of the newer materials like carbon nanotubes. They have very low surface energy, so this makes the bonding of such fibers to the matrix materials extremely difficult. So the only way to make that different is by what is called in chemical parlance, it is called functionalization, or you have to modify that surface. And in many cases, what you will find is that there are different ways to do it. Um, so one way is to treat those fiber surfaces with a plasma. Plasma is a reactive gas, and that gas will go and etch away some parts of the fiber surface, create a very rough surface, or some kind of uh, some kind of ridges in it, and those ridges can cause the matrix to go inside and bond with that and still hold it together to give it a stronger bond than if you didn't have any kind of interface at all. So in the case of plasma, it has ionized particles or dissociated molecules, and you can have plasma created under different kinds of gaseous conditions. So in the case of oxygen, um, the plasma is much more reactive than if the plasma was created in, say, the gas form of nitrogen. Or in the case of argon, also it's pretty reactive compared to nitrogen. So by doing the plasma treatment, you can modify the chemical structure as well as the topography of the surface of the material or the fibers. And it removes also the surface contaminants and highly oriented layers. It then adds polar and functional groups, like, if you are going to be reacting it with an epoxy matrix or something like that, it will create hydroxyl bonds or carbon double bonds and things like that, that will then react with the matrix itself. It also introduces some kind of ridges and forms surface roughness, so the matrix can go inside those rough areas and cause some kind of a mechanical interlocking. So by doing that, by increasing the by creating all these ridges and things like that, you are going to be increasing the specific surface area by 3 times by plasma treatment. But which means you have to do this for a very, very long time. So if you have to make sure that you do not make the fiber surface extremely rough, then you won't get the same kind of um, interlocking forces like in that case. So in the case of aramid fibers, you can react it with sulfuric acid, acetic acid, anhydride, or methacrylol, chloride, etc. Or you might react it with sodium hydroxide. Or then you have to react it with some kind of a amino groups um, that will then react with the matrix itself. Or you might react it with bromine water, or you might do plasma treatment with ammonia or argon in vacuum. So by doing ammonia, what you are going to be doing is you are going to be attaching amine groups, and those amine groups can then go and react with the amine groups in the matrix itself. But when you do the plasma treatment, you are going to be losing the tensile strength of the aramid fiber itself due to the etching of the fibers. So you have a balance. You do not want to do plasma treatment for a very long time. You do that for a very short time, stop it, start again, stop it, start again, and things like that. So by doing that, you are going to be getting a highly reactive fiber surface with reasonably good tensile strength for the fibers. If you are going to be taking, say, ultra high molecular weight polyethylene fibers, which is what you get in the market under the trade name Dyneema or Spectra, which is used in bulletproof vests and things like that. So chemically it is very inert and it does not bond well or easily with any polymer matrix. So then you etch those fibers either with chromic acid or you do plasma treatment again, or you might uh, do that in presence of a cold gas like air, ammonia, argon, etc. Then the plasma can modify the surface in minutes. The interface is much more important in the case of carbon fiber composites. So the reason is that, again, just like the other fibers, the carbon surface itself is not that expensive. So one thing to note is that carbon fibers is extremely inhomogeneous. Its strength in the tensile direction is very high, but in the thickness direction it is very low. And this is because you have these basal planes and they are rolled up like a paper roll. And these basal planes can be very graphitic, extremely smooth. It is weak in shear, and because of all this, it is also very hard to bind within a matrix. So you need surface treatment to increase the surface roughness as well as increase the surface reactivity. So let me stop here for this section and upload this one, and I will start again later.